Hello PCHers, welcome back from spring break. I hope you had a good time. I am writing this before or recording this before spring break, so I may be a little tired. All right, so you have looked at finding determinants and using Kramer's rule, and what we're going to look at today is inverses. And we're going to probably only be working with inverses of 2 by 2s because as you get larger, it is a more complex manipulation. And we're really just trying to give you an intro into what are matrices. So we've already looked at what the identity matrix is. We looked at something where the result was the identity, where you have ones on the diagonal and zeros off the diagonal, and it is always going to be a square matrix, so 2 by 2, 3 by 3, 4 by 4. Notice that they all have ones on the diagonal. And if you go further into matrices, you'll find there's something called Gauss-Jordan reduction, where you take a matrix and you turn it into this identity matrix, and the result in another matrix is the actual solution of a very complicated system of equations. So they can be very powerful, but again, we're just going to be kind of scratching the surface here. So let's look at some of the properties of the identity matrix. If I have a matrix A and I multiply it by the identity matrix I, you get back A, which kind of makes sense. It's like multiplying by 1. So just to do a little bit of review again, because I know it's been a long time. And let me also say, in this case, it would also be commutative. So the identity matrix times A would also give me back A. It wouldn't matter which order you multiplied it in. As opposed to, hopefully you've noticed, order does matter when you are multiplying with matrices. So notice here, I have 3, 5, negative 2, 1, multiplying against 1, 0, 0, 1. So if I multiply that out, remember you're doing rows by columns. So this first row by this first column would give me 3 plus 0. So it's just going to leave me with 3. Then if I do the first row with the second column, I'm going to get 0 plus a negative 2. So that position will be a negative 2. You can kind of see it's already happening. So now we go to row 2 with column 1. So that's 5 times 1 plus 1 times 0. So that leaves me with 5. And lastly, we have row 2 with column 2. So we get 0 plus 1. And you get back the matrix that you started with. Okay, so we have the inverse matrix, which is what we want to be looking at. Has that same notation as your inverse sine, inverse cosine, sort of that exponent of a negative 1. And if you multiply the inverse times A, you get back the identity matrix, which means they would be inverses of each other, which also means I could also multiply A times A inverse. However, I recommend we stick with putting that inverse in front, as you'll see when we get into start solving, because order will matter when you multiply the inverse by a different matrix. Okay, so let's look at what happens if I multiply these two matrices together. So we're going to do our row 1 with column 1. I'm just going to kind of put an arrow there. So row 1, that would be negative 3. I'll kind of write it out in case you're a little rusty. Negative 3 plus 4 times 1, which is 4. Then we're going to have row 1 with column 2, which will be negative 4 plus 4 times 1. Then we're going to move to row 2 with column 1. So that's going to be 3 plus a negative 3, and then row 2 with column 2 will be a positive 4 minus 3, and when we simplify that out, you get 4 minus 3 is 1, negative 4 plus 4 is 0, then we have a 0, and voila! So that means I could call this A inverse, I could call this A, and we got ourselves the identity matrix. Now, it doesn't matter which order you multiply the inverse by itself, you will still get the identity matrix, okay? So in other words, they are inverses of each other. Now, how do you get that inverse? So we just did an example where we were given the inverse. What we want to investigate is how do you find the inverse, and then what do you do? What good is an inverse? So let's look at this. Here is the process if it is a 2 by 2, because it gets, like I said, a little more complicated when it gets larger. So with a 2 by 2, your matrix has potentially in this position A, B, C, D. So here, to find the inverse, you are going to have a coefficient, which is the reciprocal of the determinant. Remember, that's what your determinant of A would look like, A times D minus B times C. And then what happens inside the matrix is A and D will switch positions, B and C stay where they are but are negated. So here's sort of a outline of the steps. And once you do it a few times, you sort of get used to the process. It's not terribly difficult. So if I was going to find the inverse of this, first thing I usually do is, so it'll be 1 over my determinant, which will be 3 times 1 minus a negative 10. And then we would have the 3 and the 1 will switch positions. 5 will become negative and 2 will become positive. And then we distribute the determinant. So the final inverse would be 1/13. And then we have 2/13, negative 5/13, and 3/13. And then that would be A inverse. And if you wanted to verify that that was in fact the inverse, you could go through the process, let's just do it. Well, if I multiply A times A inverse, you should get back your identity matrix, 1, 0, 0, 1. Okay, so let's just do a couple examples. Again, you start off, let's call this matrix B. So I'm going to start with 1 over the determinant, which is going to be 10 times 10 minus a negative 7 times a negative 14, which is a positive 98. And then the matrix itself, well, 10 and 10 switch positions. That was interesting. And these will get negated. And then you distribute everything through. So that'll be a 1/2 down here. So we're going to end up with 5, 7/2, 7, and 5. And if you wanted to verify, once again, you could multiply the two together and you would get your identity matrix. And we might during class, but just for the sake of the video, I'm going to leave the verification to another time. But I will label this. This is my B inverse. All right, so let's try this other one. Let's call this one D. And so D inverse would require me finding my determinant first. So 8 times 3 is 24, minus 4 times 6, which is also 24. Ooh, that's not good. You're not allowed to divide by 0. So what happens is you don't always have an inverse, just like you don't always have a solution to a system of equations. So in this case, no inverse is possible. And that is why I always do the determinant first, because it's the determinant that is going to pretty much define whether you have an inverse or not. And you won't have one whenever that determinant equals 0. All right, so we cannot divide by 0. All right, well now let's take a look at what do we use the inverse for. So the inverse is also a way, well, you use inverses when you are solving equations. 5x equals 10, I divide both sides by 5, which is the inverse, the multiplicative inverse of 5. And so inverses work the same way. If I have a system of equations like I have right here, The beauty of matrices, it's kind of like shorthand. You don't have the x and the y, so I pull off all the coefficients and put them into what is called the coefficient matrix. Kind of makes sense. And you then have your x and your y, as we have here, called the variable matrix. And then you have your constants, because these have no variables on them, or your solution. I've also seen it written as, and so that is here, my constant matrix. So you can, if I called this A and called this x equals B, I've got an equation here. Now I want to isolate x because I'm trying to solve for my variables. So what you're going to end up doing is multiplying both sides by the inverse of A, because we know that A inverse times A would cancel each other out to be the identity matrix. So here's how the steps would work. I kind of have it written down here. You start off with A, your coefficient matrix times the variable equals your constant. So then we come up with the inverse, and notice we're multiplying it in front for both sides. And we know that A inverse times A is the identity matrix. And that identity matrix is just going to be whatever x ends up being when you multiply it. So your solution will be the inverse of A times B. All right, so let's put it into use. Let's do this. All right, so we're going to start off by writing our system. And I'm trying to look at, oh, I shortened things down here. Okay. So I have, this is a different problem than what I had before. So let me just write it out. So here's my coefficient matrix, 7, 3, 5, negative 2. Oh, I guess this is the same as what we had up above. I didn't realize that. Sorry about that. That's fine. So 3, 22. So that's how I would pull it all together. Now, if this is A, I need to find A inverse. So A inverse is going to be 1 over negative 14 minus 15, because that's the determinant, cross multiplying. Then we switch the negative 2 and the 7, and we negate the negative 3 and the 5. And so that is going to be my inverse matrix that is going to be multiplied against 322. Because we're going, this all is A inverse times B. That's going to give me my solution. Now, sometimes it kind of depends. If my determinant, like this one's going to be 1 over a negative 19, which is kind of ugly, so I leave that out until the end, and I just multiply my integers first. So what I'm going to have in the end is 1 over a negative 19, and then I'm going to multiply this out. So I have a negative 2 times 3, so negative 6. I'm going to write this out. I'm too tired to carry things in my head. So negative 6, and then plus a negative 5 times 22 is a negative 110. And then we're going to have, so that was row 1, column 1. Now row 2, column 1, negative 9. Plus 7 times 22, which is 154. And so this gives me, so I'm going to have negative 116 divided by a, oh, I'm so silly. That was a negative 29. Sorry about that. Okay, 14 and 15. That's how tired I am. Okay, so we have negative 116 divided by negative 129, believe it or not, is a very friendly 4. And on the bottom, we have a positive 145 divided by negative 129, gives me a negative 5. And that would be the solution. So we know that x equals 4 and y equals 5 in my system of equations. And I know that looked like it took a long time, but we're also going to show you, if we have time, how to do some of this on the calculator, which really just then does everything for you. I do know a lot of colleges are not letting students use graphing calculators, which is why we're trying to teach you first how to do it by hand and then go from there. Okay, so you now have two ways to solve systems of equations. Actually, Cramer's rule used to be taught in Algebra 1. I think it's kind of a shame we don't anymore. But we're going to solve the same system of equations two ways, and then you decide which way you like better. So the first one, we're going to do it by inverses. So I'm going to go to 3, 1, 2 times xy equals 0, negative 2. So we want the inverse of this. So that's going to be 1 over 4 minus 3. Oh, that's a nice determinant at least. We're finding our inverse. And so then these two switch positions, negative 1, negative 3. That is going to get multiplied by the constant matrix. And the end result is going to be, so we're going to have 0 plus 2, and then 0 minus 4. And that is going to equal our xy. That was really easy. Then you had Cramer's rule. Remember, Cramer's rule is where you first find the determinant of your coefficient matrix, which we already kind of did that, so we know that that's going to be 1. Then we find the coefficient of our x matrix, which we replace. Remember, you replace the constants if you're solving for x. Keep the 1, 2. Notice I'm also using the straight lines. So that determinant is 0 minus a negative 2. And the determinant of the y, now we keep the first column and replace the second column with our variable matrix, constant matrix, 0, negative 2. So that gives me a negative 4 minus 0. And since you're going to be dividing that by the determinant of the matrix, we know that x equals 2, y equals negative 4. It's kind of an easy example, but it gets the point across. Okay, so you have two different ways to solve a system of equations.